Hello, students. Today, this lecture is going to discuss energy changes during phase changes. So after doing the phase change of water, we now know that a phase change diagram for a pure substance is going to look similar to the one displayed here. And this is true for any pure substance, not just water. We're going to look at this in a lot more depth today. Why does the diagram look like this? Well, why does the temperature rise when a particular phase of matter is being heated, but and then remain fairly constant during a transition from one phase to another? First of all, let's look and see what is happening here. Between the region of A to B, this region here, we have a solid. And we can see that as we add heat over time, the temperature rises in that solid. But then when we get to B, from the region of B to C, in this area here, we have no temperature change. And that's at the point that's indicating a phase transition. Phase transition here, we have solid going to liquid, and we call this melting. From C to D, once again, the temperature is increasing. The temperature of the substance, whether it's water or whatever, as we increase the amount of heat over time added. So we see this temperature increase. Here we have liquid, and the liquid is just getting hotter. In the region between D and E, this region here, no temperature change is occurring here. Again, this is another phase transition or change of state of this substance. Here we have a liquid changing into a gas. We call this boiling. Another term for this is vaporization. And then finally, in the region between E and F, here, temperature is once again increasing as we increase the amount of heat added. And this is where we have the gas phase, and the particles in the gas phase are just increasing in temperature. So in order to understand what's going on here, we really need to review the energy and kinetic molecular theory reading that you were assigned earlier this week. So the first of all, the most important concept I want to get across here is that energy is not a substance. Energy does not have mass. Energy does not take up space. But thinking of it as a substance is kind of convenient for visualizing what's happening. So we use substance as a metaphor to describe energy. There are three principles that are involved to help us form a concept of energy. And the first is, again, that we see energy as a substance-like quantity that's stored in physical systems. Okay, so matter is involved here. Okay. Energy can flow from one system to another and thereby cause change in matter. So that's how change in matter occurs, by energy moving from one system to another. And then third, energy is just energy after being transferred. It maintains its identity. It's conserved We all know this now. There was a law of conservation of energy. It's neither created nor destroyed, nor does it really change forms, although oftentimes in your education so far, you've been taught that energy exists in different forms. We're going to try to move away from that idea and just think of energy as energy. It's transferred differently and it's stored differently. And I'll go into that next. So another way to think about energy is what else do we know that is hard to define, hard to put our finger on? Energy is kind of like information. Information can be stored in various ways. It can be transmitted in various ways. Um, Energy is being stored in this video. It's transmitted through you hooking up to YouTube to watch this. Energy is like money. You can have money um, stored in your credit card. It's stored in your checking account. It's stored in the cash that you have in your wallet. But none of those are really the money itself. Those are just ways of storing the idea or the concept of money, a quantity of money. Okay. In that reading, you read that there are 3 ways to store energy, 3 accounts, if you will. First of all, there's thermal energy, and we talk about thermal energy and we abbreviate it with the ETH. This is the energy of that's stored in moving particles. And this way of storing energy is related to both the mass and the velocity of those particles. Okay. The phase energy is abbreviated as EPH, and that's the energy stored in a system due to the arrangement of particles. Okay. So in phase energy, the gas, for example, would have the greatest amount of phase energy since the particles are completely broken away from each other. It depends on how much attraction there is and how much repulsion. So for this, an attraction is going to reduce or lower the EPH. Repulsions are going to increase the EPH. So once again, now you can see why in the gaseous phase, those particles are going to have the greatest amount of stored energy as phase energy. All right, and our last way of storing energy that we're going to consider in chemistry is chemical energy. And this is energy that is stored by the attraction of atoms within molecules. So the difference between these is this is between particles. Those particles could be molecules. This is within particles. If those particles are molecules. Okay. There are 3 ways that we're going to consider for transferring energy. And this is the way energy flows. And we like to put the ing endings on these terms to give you the sense that something is happening here. So the first one is work. And work is macroscopic forces, such as big things, macroscopic objects. Exerting, that's an X, exerting forces on other objects. In one of your readings this week, you had a diagram of a picture of a man on a hill pushing a ball down the hill, giving it a push so the ball would roll down the hill. So the man was exerting force on this ball. He was doing work on the ball. The ball rolled down the hill and hit a ball that was at the bottom of the hill, causing that ball to roll up slightly and come to a resting position a little higher up on the other side of this hill. And so the first ball A, when it hit ball B, did work on ball B to give it a shove and put a force on it to move it up the hill. Okay, the second form of transfer of energy is heating. And we symbolize this with the letter Q. We're going to be working with Q a lot next week, so remember that letter for heating. We're familiar with this. We used this method of energy transfer to cause the phase transition between ice to the gaseous phase of water. And then the third form of transferring energy is by radiating. And we mentioned this earlier in the year, that radiating is energy transfer by absorption or emission of photons. Photons are packets of light. Sometimes they're referred to as particles of light. We don't normally consider light to have particles, but there are particular aspects to light as well as wave aspects. You'll learn more about that in physics class. But radiating is the absorption or emission of these particles of light. So when we turn a light on, the bulb is emitting photons of light. Okay. So there are three principles of the kinetic molecular theory that are critical for this unit. And the first of them, and we've talked about these before, is that matter is made up of nanoscopic particles that are in constant random motion. This should be very familiar to you. Second one is that particles exert long-range attractions and short-range repulsions on each other. And we mentioned earlier in this lecture that attractions will reduce the phase energy and repulsions will increase that phase energy. And then the third thing is that a hotter sample has on average faster moving particles than a cold sample has. Again, you should be very familiar with this at this point. Now let's return to the phase change diagram. First of all, to convert solid water to gaseous water, we had to supply energy to the system by which transfer mode was that? You should all be saying heating with that ing on the end, and the letter that we used to represent heating, again, was the letter Q. Hopefully you all got that. How is that energy being stored here? What change is occurring in the matter in these different portions of the phase change diagram? Well, let's take a look at the region from A to B. We have a temperature increase as we increase Q. Q's increasing here. The temperature's increasing. So there is an increase here in the ETH. The particles are moving faster. So the solid, remember this was the region where we had solid. The particles of the solid are moving faster. What happens between B and C? In this region, there is no change in temperature. So there is an increase here in the phase energy, EPH. And at this point in time, we see that what is happening at the particle level is that the particles are moving further apart from each other. There is a repulsion going on. Particles are moving apart. As the EPH increases, it's overwhelming the attractive forces that hold those particles together. What's happening between C and D? Again, we have an increase in the ETH. How do we know this? The temperature is rising. We have liquid here. The particles of the liquid are moving faster. And then we have another region from D to E where there is no temperature change. There's an increase in the EPH again here, which means that the particles once again are moving further apart. Particles are moving apart even more. So in this region here, we have the particles that were held together by some attractive forces as a liquid now moving farther apart. Those attractions have been overcome. There's more repulsive forces, and the particles are moving farther apart with an increase in the EPH. So liquid is transitioning to gas. And then lastly, in the region between E and F, we have gaseous particles. The temperature is increasing, so we have an increase in the thermal energy of those particles. They are just moving faster. Okay, let's summarize what we've talked about so far. In a phase change diagram like that, when we take a solid, pure substance and we heat it over time to get to a gaseous substance, energy is being transferred to the water or whatever pure substance by heating. And again, we represent heating by the letter Q. While heating the water in a particular phase, so if we're in the solid phase, for example, energy is transferred into the thermal energy account, if you will, of the water. The particles are moving faster, as indicated by an increase in the water's temperature. During phase transitions, here, either by boiling at the boiling point or at the melting point, energy is transferred into the phase energy account of the water. The attractive forces holding the particles together are broken, and the increase in particle energy overcomes the force holding the particles together, and there is greater repulsive forces. Increase in repulsive forces. And that ends this lecture. We will talk more about why there's no temperature change during the phase transitions later next week.